We can do a lot of this. We can zip through this. We've already done functions similar to this. Would you agree that the symmetry on this one is going to be odd? Top is odd, bottom is even. So overall, it's going to be odd. So we know we're getting odd symmetry, or I can just do my test for symmetry. The domain is x cannot equal plus or minus 1. Those are vertical asymptotes, aren't they? Those are zeros of the bottom, but not the top. We get odd symmetry. Now, what about, before we jump into the calculus here, what about the limits at plus or minus infinity? Okay, this is a case where if I take the limit of this function, the top is bigger degree than the bottom this time, right? So the top is going to grow faster. So there is no horizontal asymptote here, agreed? Okay, but what is there? Okay, if the top is exactly 1 degree higher than the bottom, then this is going to give us a slant asymptote or an oblique asymptote, whatever you want to call it. And we have to just divide this out, right? So how can we divide this out? Let's remind ourselves how we do this. It's been a little while since we've done this, but this is pretty good stuff to review. So we could divide this out using long division. That's fine. We could also divide this out using synthetic division too, if we wanted to, right? Take your pick. How about if we just let's use long division on this, because why would we gravitate to long division on this? Yeah, right, because you can only use synthetic division where you have linear factors of the denominator, right? And so you could make it work, but it's a little awkward to do. I don't want to take the time to do it today. Maybe later on we'll come back and I'll show you. I'll remind you how you could use repeated synthetic division on this. But for now, let's just use long division. So if we divide x squared minus 1 into x cubed, which is really x cubed plus 0x squared plus 0x plus 0, right? What do we get here? So x squared divides into x cubed how many times? X times. Remember, that's always how we do long division. We're dividing the leading term in the denominator into the leading term in the numerator. In other words, x times what is x cubed? X. So I distribute the x. X times x squared is x cubed. X times -1 is negative x. And now I'm going to subtract vertically, right? So it's a good idea to put this in parentheses and put a negative out front. So you remember you're subtracting the whole quantity. What's that give us? These cancel, of course. X cubed minus x cubed cancels. 0 minus negative x gives me a positive x, which is my remainder, because x squared won't divide into that. And so what's this equal to then? This is equal to x plus x plus my remainder of x, and it remains over my denominator, right? And so now if I take the limit of this, the limit of x plus x over x squared minus 1, as x approaches plus or minus infinity, look what happens. I get this rational function here where the bottom is bigger than the top. So that rational function in the infinite limits, as we approach plus or minus infinity, that goes to 0. And so I'm just stuck with my limit is equal to x. So my slant asymptote is the line y equals x. Okay, and that's where we'll leave off for today. So my slant asymptote y equals x. Okay. All right. Keep going on this stuff. We got one more day of this. I want to go through a few more of these, and then we're done with this section. Okay. This is a huge section. There's a lot going on. Have a great day. I'm here after school if you need me. Natalie, email me. Okay. Through this. So we started this one yesterday. Last rational function we're going to see. I wanted to do one of these because we had a case here where the degree of the numerator is 1 bigger than the degree of the denominator. And remember, in that case, there are no horizontal asymptotes, but there is a slant asymptote or an oblique asymptote. And how did we get that? Well, we just had to divide this out and simplify it, right? Simplify the quotient. When we did our long division, we found out that the quotient of x cubed divided by the quantity x squared minus 1 gave us x with a remainder of x. So plus x divided by my denominator, x squared minus 1. So in the limit then, when we take the limit at plus or minus infinity, the remainder part of that is always going to end up being a rational function where the denominator is a bigger power than the numerator, right? And so that's always going to just go to 0 in the limit, and we just end up being left with whatever the terms are that we get before the remainder. Whatever those terms are, those represent the line that is creating our oblique asymptote. So in this case, we just get the line y equals x. Okay. So then going back to our, to our page here, we got a slant asymptote at y equals x. What's going on at our, we had to remove two values from our domain, plus and minus 1. Type in chat for me real quick. What's going on? What's interesting about what's happening at x equals plus or minus 1 for our function? What's going on there? Okay, good. So we got vertical asymptotes. Good, good, good. Okay. And then all we have left to do here is just do some differentiation, right? We got to find the values of the derivatives, so we can find some critical numbers, and that's it. We can already add a few things to our table. I'll tell you what, let's not do that until we differentiate, though. I'm going to erase this, too. We did this on the other page, so I just want a little more room here. So if we differentiate, this is just another example of quotient rule. I'm going to go through this a little quicker. I've had you guys go through a bunch of these. You can all do quotient rule. So we get low-d high, x squared minus 1 times 3x squared minus high-d low. So x cubed times 2x divided by the bottom squared, so x squared minus 1 quantity squared. And what's that give us then? So we're going to get 3x to the 4th minus 3x squared minus 2x to the 4th. So that's just going to be 1x to the 4th minus 3x squared, right? Divided by x squared minus 1 squared. Give me a thumbs up if I did that right. Okay, you guys got to check my work here. Okay. So I could factor that a little bit more. On the top here, it looks like I could factor out an x squared, leaving me with x squared minus 3 divided by x squared minus 1 quantity squared. So what are my critical numbers then for the first derivative? The first derivative is nowhere undefined in our domain, right? Because the only places where the first derivative is undefined are places where our function is undefined. So those aren't critical numbers. Those don't count. But we do get a couple critical numbers. We know that f prime equals 0 at x equals what values? Type them in chat for me. Where's our first derivative equal to 0? Okay, good, good. So we got x equals 0 or plus or minus the square root of 3, right? From this factor, and then I get 0 from that factor. Okay, good. Second derivative. And we'd probably want to use this part right here, wouldn't we? We don't want to use this part because I don't want it factored when I'm doing a quotient rule derivative, because then I've got product rule on the top and that's too much, right? We'll use this version of the derivative right here to take our second derivative. Everybody give me a thumbs up. Does that make sense? That's going to be the easiest one to differentiate. Okay. And so then let's see, we're going to get y double prime. Again, I've just got quotient rule. So I've got low d high. D high is going to be, what are we going to get here? So I'm going to get 4x cubed minus 6x minus high x to the fourth minus 3x squared d low. And that's a chain rule issue, isn't it? On the bottom, when I differentiate the bottom, I've got a hand squared, so I've got to do 2 times hand to the 1 times the derivative of hand, which is 2x, all divided by the bottom squared. So x minus the quantity x squared minus 1 squared squared is to the fourth. Everybody agree? Okay, let's do something. Now, here's where we factor out. We try to factor the top and cancel like terms and things like that, right? So what are some things we could factor out of the top? What are the bases that could be factored out of the top?
X squared minus 1.
Okay, so one base is an x squared minus 1, right? So and I'm going to be able to only factor out a single x squared minus 1 from both of those. Okay, so let's abbreviate our work on this one, and let's just do this. I'm going to effectively factor out an x squared minus 1 and cancel it with 1 on the bottom. Everybody see what I did? Okay. So it's all the same stuff we've been doing, but we could just make the work a little bit more concise on that one. So there's still, now what can we take out? Well, it looks like we could take out maybe a 2x. Everybody agree? Looks like I could take out a 2x because I could factor a 2x out of here and I could factor a 2x out of there, right? So I'm going to get a 2x, and what am I left with if I factor out a 2x? So here I've got an x squared minus 1. Yeah, I'm going to have to go down to the next line. That's going to be too hard to read. So we'll take out that 2x. And then what am I left with? So here's the minus sign that's separating the two terms from quotient rule, right? So what about this first term? I've still got an x² minus 1 factor. And then if I take a 2x out of this pink factor here, what am I left with? Well, I'd end up with, what, 4x³ divided by 2x would give me a 2x², right? Minus 6x divided by 2x, that would just be, end up with a 2x² minus 3. Everybody agree? That's what this factor is giving me. If I factor out my 2x, give me a thumbs up so far if that makes sense. Okay, questions on that? Okay, looks like, any questions on that step? Okay. And once again, all I'm doing here is I'm factoring out this 2x, right? That's what I'm factoring out of each of these two terms. So now what about the other term? The term to the right of my minus sign. Well, if I take a 2x out of that, it's pretty easy, right? That 2x is just gone, right? That guy goes away, and I'm just left with everything else, right? Well, that's gone, so I just get 2 times the quantity x⁴ minus 3x². So what's that give me if I distribute then? I'm going to get a 2x⁴ minus a negative is plus 2 times 3x², so 6x². All divided by x² minus 1³. So now we just have to clean up a bunch of stuff. So I've got my 2x out front. What if I expand all this out? What am I going to get? So if I FOIL that out, I'm getting 2x⁴, 2x⁴ minus 3x² minus 2x² is minus 5x² plus 3. So if I FOIL out those binomials, I just get that, right? And then minus 2x⁴ plus 6x², all divided by x² minus 1³. And look what happens here. The 2x⁴s cancel, and I could combine some like terms. Negative 5x² plus 6x² is just x² plus 3. So I got my 2x times, and in here I'm just left with an x² plus 3, all divided by the quantity x² minus 1³. Okay, so again, the second derivative is nowhere undefined in our domain, but where is it equal to 0? Type it in chat. Where is the second derivative equal to 0? Now I've got it in factored form. Again, where is that second derivative equal to 0? Okay, good, just 0, because x² plus 3 is not equal to 0 for any real, there are no real zeros of that factor, right? We're looking for real zeros. So we just get 0. So now we can start making our table. We've got, put our critical numbers in there. So we had critical numbers of the first derivative at 0 and plus or minus square root of 3. So that was a 0 of, these are all zeros of the first derivative. 0 was also a 0 of the second derivative. We had some asymptotes. We had asymptotes at plus or minus 1. Function was undefined there. We determined those were vertical asymptotes. And we had a slant asymptote at y equals x, okay? Our domain was everything except -1. And +1. So now what? Yes or no, can I use the second derivative test at x equals negative square root of 3? Yes or no? So again, my question is, can I use the second derivative test? I'll type it in chat. Here's what I want you to respond to. Give me a yes or a no there. Okay, what is the second derivative test? Somebody refresh our memory. What is the second derivative test? What's the second derivative test? Kyle, what's the second derivative test?
When you plug it back into the second derivative and see if it's positive or negative.
There you go. Good. So the second derivative test, remember, is a test for critical numbers, right? Places where critical numbers where the first derivative is equal to 0, okay? So if I have a first derivative equal to 0, which I do at negative square root of 3, then let's start to build our little picture of what's going on there. So I know I get a horizontal tangent. This is a place where I can apply the second derivative test. I just need to know the sign of the second derivative at that first derivative critical number. And that's going to tell me the outcome of the second derivative test is, you know, if it's a minimum or a maximum, right? Okay. So yeah, I can apply it there, right? The answer is yes, I can apply it there. I can also apply it here, can't I? At positive the square root of 3. So we just need to evaluate our second derivative at negative radical 3. So what do we get here if we do that? If I do f double prime of negative the square root of 3, what do I get? Negative times positive over positive, right? Everybody agree? So that's negative. I get negative over positive is negative. So what is that then? Type it in chat. What's going on at x equals negative radical 3? What is that? What kind of an extremum is that? Okay, good. That's a max. Good. How about up here at positive the square root of 3? That's going to give me positive times positive divided by positive. So that's positive second derivative. So then that's going to be a minimum, isn't it? Okay, yes or no? Can I use the second derivative test at 0? That was my other critical number. Yes or no? Can I use the second derivative test there? No, you're right, I can't. It fails because the second derivative is equal to 0 at that critical number. So remember what our rule of thumb is on that. If the second derivative fails, we revert to the first derivative test, right? So in order to use the first derivative test, what do I need here? What am I going to need? Lily, what am I going to need here to use the first derivative test?
It can't be a maximum, right? Is that why?
Well, okay, so we don't know. And here's something else I want to reinforce. Because I've got these vertical asymptotes, the vertical asymptotes change everything, right? I mean, the function is completely disconnected surrounding these vertical asymptotes. The vertical asymptotes like wall off the universe for this function so that they're completely separate little universes, right? Anything can be happening between those vertical asymptotes. It could be a minimum, it could be a maximum, it could be neither. We don't know. You can't look at, and I know what you're doing. It was a smart thing to think about. You were thinking about, well, if this is a minimum and that's a maximum, how could you connect those with another extremum in the middle, right? And you couldn't if those weren't vertical asymptotes. Maybe I'm putting words in your mouth, but I imagine people were probably thinking this. If I've got a maximum here and a minimum here, there's no way I could have another extremum in the middle, just one, and connect those things, right? Except, remember that we've got these vertical asymptotes here, so all bets are off. Okay, so we could have something else going on there. What do we have to do, though? Remember, let's just do a quick review of the concepts here. The second derivative test, we already kind of discussed it, right? The second derivative test is the one where we're just going to evaluate the second derivative at a 0 of the first derivative. It's the most convenient one to use if we have a second derivative and we don't have a 0 of the second derivative, okay? But lots of times in real calculus, when we're actually doing calculus to accomplish something, either we don't want to take the second derivative because we don't care about it, or we have something like this where we did take the second derivative, but it fails. So the first derivative test, remember what that one does. The first derivative test is just saying, if I know the sign of the first derivative at test values surrounding my critical number, that constructs a picture for me, right? If I go, like, if I'm going from, for example, I know that if I have a critical number, just real quick here. If I have a critical number out here at 1, for example, where I have a 0 of the first derivative. Well, if I pick some test points, if I picked like 0 and 2, if my second derivative were positive here and negative there, that means I'm going from an increasing function to a decreasing function. So it has to be a maximum. Remember that? Right? Everybody remember? So that we're using the sign of the first derivative at test values surrounding a critical number to determine what kind of an extremum is that critical number. Okay, but what's the problem with this guy here now? I mean, it's not a problem, but what do we have to be? We have to pick test points, but where would the test points have to be located? Okay, good, right. They have to be, right, the critical numbers have to be inside the asymptotes, but surrounding the critical number, because the vertical asymptotes just wall off the function. So it doesn't do us any good to pick a test point on the other side of the asymptote, because that's not really telling us much, is it? it's going to have to be inside the asymptotes between -1 and 0 and between 0 and +1, right? So we'll pick something like, oh, I don't know, we'll just pick something like, for example, how about if we pick like -1/2 and +1/2, something like that. And we're just going to test the signs of the first derivative there. Okay, well, here's our first derivative in factored form, right? So let's do a quick little calculation up here then. If that's our first derivative in factored form, f prime of 1/2 is going to be what? Well, I'm going to get, would everybody agree, positive times negative. Bottom is always positive because it's being squared, right? But I'm going to get positive times negative over positive is negative, right? And the same thing would be true at -1/2. I'm going to get positive times negative divided by positive. So at both of those two places, at +1/2 and -1/2, I'm getting negative first derivatives, right? So is that a critical number? I mean, sorry, is it an extremum? Yes or no? Type it in chat. What's that first derivative test telling us? Yeah, it's not an extremum, right? Because we're going from a decreasing function to a decreasing function. In order for this to be a minimum or a maximum, it has to be a point of transition of the second or the first derivative. It has to either be going from decreasing to increasing or increasing to decreasing. And it's doing neither one of those things. Okay, we know though that this has a horizontal tangent, right? Because the first derivative is 0. What's the only way that that can go from decreasing to decreasing through a horizontal tangent? Well, it's got to be an inflection point then, doesn't it? And we could also figure that out. I mean, did we have to use this row? No, we could have used the second derivative row also if we wanted to. We don't have to do either, we don't have to do both of those. We can fill in some blanks. But if I had used the second derivative row, I could have come up here and that was negative. Let me just fill in some notes here for you. So we already figured that stuff out. What if I did f double prime of -1/2? What's that going to give me? Negative times positive divided by negative, right? Because the bottom is being cubed. So -1/2 squared minus 1 is negative, cubed is still negative. So that's giving me positive. If I evaluate the second derivative at 1/2, I'd get positive times positive divided by negative. So I'd get negative. So this would be a change in concavity, right? From positive to negative with a horizontal tangent. Either way, I'm getting an inflection point, aren't I? Right? Okay, is everybody seeing that? And once again, I'm going to put the word or in here because I really don't have to do both of those. By evaluating the signs of the test points, either using the first derivative row or the second derivative row, it tells us everything we technically need to know there, right? Okay, so there's a lot to these tables. I mean, it just takes practice. Do you feel like, are we kind of getting there with the tables? I guess let's do our sketch real quick too. And then I'll ask that question. So if we do our sketch, what's this thing going to look like? So here's x equals 0. There's our y-axis. Here's our x-axis. Do we want to evaluate this function? Is it easy to do? Not really. That's going to give us 1 on the bottom. So I'm just going to get 3 radical 3. So, well, if I were to do these derivatives. What am I getting here? 2. The y values would just be 3 radical 3 over 2 here, and they'd be negative 3 radical 3 over 2 there, unless I made a mistake. But that's not, we don't really care about that much. And at 0, my function is equal to 0, so that's nice. Okay, and I've got some asymptotes. So that's going to be like 1's right there. 1's right there. So there are my vertical asymptotes. I've got a maximum down here at negative radical 3, and I go down a little bit. It's a negative value, and that's a maximum, right? And then over here, I've got a minimum. I forgot one asymptote, though, right? I've also got this asymptote. Oh, why does it keep doing that? I've also got the asymptote y equals x, which looks like that, right? That's my slant asymptote, okay? So then we could connect all these dots, couldn't we? We know that I've got a minimum here, and it's got to stick to these 2 asymptotes. What's the only way I could graph that function? Well, the only way I could graph this thing would just be like this, wouldn't it? Right? And then over here on this side, if it's a maximum, and I've got to adhere to these asymptotes, it's going to do that. And in the middle, it's going through the point 0, 0, and it's an inflection point going from positive to negative. Whoops. So it looks like that. Okay, visually, does this thing have any symmetry? We forgot to check the symmetry. Does it have any symmetry? Remember, even symmetry would be reflecting symmetry about the y-axis. Odd symmetry would be rotational symmetry about the origin. Good, so it's rotational, isn't it? Yeah, it's rotational about the origin, so it is odd symmetry. And we just forgot to check that, but that would have been pretty easy to check up here, wouldn't it? Because look, if we do our symmetry test, the top is odd, the bottom is even. Odd divided by even is odd, right? So I forgot to check that, but anyway, our symmetry should have been odd symmetry, which would have helped us a little bit, right? Because when we're doing our graph, then we could have just done everything to the right side of 0 and rotated it to get to the left side.